Today's lecture is going to cover the all-important topic of independence. So this is really a follow-on from the previous lecture, and we talked about conditional probability, and the kind of natural next step when talking about probability after conditional probability is talking about independence. So this idea of independence, we all have kind of this layman's understanding. And the layman's understanding of independence is basically that things don't affect each other, or if we're talking about, in particular, we're talking about two events, maybe we'd say that events are independent if the occurrence or not of one doesn't affect the probability of another. These are kind of reasonable layman's understanding of kind of what we mean when we talk about independence, but that won't do for a formal probability class, and so we have to formalize this definition of independence of events. And so let's do that. And what we'll do today is we're going to formalize the definition of independence, talk about some of the consequences, and hopefully show a little bit about how it follows our kind of layman's understanding or intuition about what independence means. So let's put down a definition of independence. I'm going to say of events, and that will make more sense much later in the class when we talk about independence of other things. But we're going to get the definition of independence of events. And so our definition is, if we have two events, A, B, they're in our sample space, we say, quote, A is independent of B, and we denote this, so I will typically denote it as A perpendicular B, meaning perpendicular meaning orthogonal to meaning independent. So these are all kind of related ideas. We say A is independent of B if following condition is satisfied: probability of AB is the product probability of A times the probability of B. So independence formally for two events is this kind of distributive law. Let's write that. It's kind of a distributive law where, and that's kind of informal, but it basically says I can distribute my probability over intersections if the events are independent. It's not quite distributive because we don't really have multiplication of sets isn't really a thing, but you see this gives a hint at notation for intersection. But typically I write my intersection as just two symbols next to each other. A and B intersection between A and B is just AB. And the reason for this notation is, I think, much more clear now when we look at independence, is if sets or events are independent, then the probability of AB is probability A by probability of B. That makes just a nice, real slick notation there. But this is our formal definition of independence. Doesn't really seem like this is capturing what kind of our layman's definition of independence is, but probabilists have thought about this for a couple hundred, well, maybe 100 years. And this is the best way of talking about and defining independence. And we'll see in this lecture that many of the other intuitions we have follow from this definition. So here we could write a theorem or some intuition that hopefully is true, and we'll see it is true. So if I have two events, A and B, and they're independent, so A is independent of B, I could look at, going back to last lecture, I could look at, say, the probability of A given B. So our layman's definition of independence says that the occurrence of A or not doesn't affect the probability of B, and the occurrence of B or not shouldn't affect the probability of A. Conditional probability is kind of giving us information. So if I say the probability of A given B, I'm giving you information about whether or not B occurred. In this case, I'm saying B did occur. And then presumably you can adjust the probability that A occurs given the information that B occurs. However, if A and B are independent, we don't expect the information that B occurred to actually change our probability that A occurred. And so what's the result that we expect to be true? We expect that we don't actually care about probability of B, or about the occurrence or not of B, and that the probability of A given B, same thing as probability of A, because B does not affect A. Now that's a much more kind of intuitive definition or result of independence. It's not how we define independence. Presumably you could more or less make that the definition, but it doesn't generalize very easily. And so we like our kind of multiplicative definition above. The proof, so it turns out this is true. This is kind of an intuition we have about how probability behaves. It's true, and we can prove it. So that's proof. This is just going to, come back. This is just going to be kind of expanding out. First, we want to use our definition of conditional probability, which says that A given B, it's probability of A intersect B over probability of B. So this is just definition of conditional. And then we are going to apply our definition of independence. And if A and B are independent, we can surely write probability of A intersect B as the product, PA, PB. Of course, we still have our PB in the denominator. Those cancel, and we get probability of A. So we get the result we want, and it's a nice little one-liner proof, which is what we like in this course. And so that's kind of, starting to justify how this definition of independence is really capturing some of our kind of layman's intuition about what independence means. Let's look at an example. Consider rolling, let's say, 2 dice. And I'm going to say independently. Typically how we think of die rolls, which is that they are independent. The roll of one die doesn't affect the roll of the other die. And I could ask what the probability of at least 1, 6. So one of the dice is a 6, or the other one is. So how would we want to calculate this? This example gives us a nice little trick, which is when you are talking about at least one, it's often easier to look at the complementary probability. So we could say this is equal to 1 minus the probability of, let's abuse notation and say at least 1, 6 complement, right? Well, what is the complement of at least 1 6? That is no 6s. That is neither of the dice has a 6. So at least one means one of the die has 6 or the other one, or they both could. Complementary would be none of them have a 6. So this is a real standard trick with independence. Why do I want to write it this way? If I write it this way, what I can do is I can actually kind of formalize what no 6s means. If I let A1 be no 6 on first roll, and A2 equals no 6 on second roll, then my event no 6s, let's say, bring this down here, my event of no 6s is no 6 on the first and, or intersection, no 6 on the second. And so I can rewrite this as 1 minus the probability of A1 intersect A2. And if I believe now, we're going to use our independence here. Once I've converted this basically into an intersection problem, that's real nice because I know I have independence, and that independence will allow me to break apart this intersection as 1 minus the probability of A1 by A2. And both of those are pretty simple to calculate, right? Probability of no 6 can move equally likely rolls. The probability of no 6 on the first roll is 1/6, and the probability of no 6 on the no 6 on the second roll. Oops, I'm sorry. Should be 5/6, right? No 6 on the first roll should be 5/6, and no 6 on the second roll should also be 5/6. And so we get 1 minus 25/36, or 11/36. That's the probability that neither of my two dice come up as a 6. And it shows a couple little tricks. It shows this complementary trick. And the reason I do that is because I want to write probability as an intersection between two independent things. And then once I've written as an intersection between two independent things, I can expand out that intersection by distributing probability over, given my knowledge of independence, given my definition of what independence means. Okay, so this is a problem we can solve kind of with independence that way. We could also look at it from a counting perspective. So let's look at how you could solve this problem from a counting perspective. So here, I could think of this as sampling from the numbers 1 to 6. So that is n is equal to 6 2 times. So r is equal to 2 samples. And we can think about doing that with replacement. This is not like we can get 2 6s, for example. Not like if I get a 6 on the first roll, I can't on the second roll. And then we have a choice. And this is a choice that you've probably come across in doing some problems for the counting section. And that is, do I count this in an ordered way, or do I count this in an unordered way? So I had a kind of lengthy comment 2 lectures ago, at the end of kind of 2 lectures ago, about proper way to solve this, and I claimed that the reason there is a correct and kind of incorrect way to solve this problem is because we wanted to respect the independence of the rolls. So let's first look at doing this in an ordered way. In an ordered way, so this is my sample space, right? I'm just thinking about what elements are in my sample space. And so in an ordered way, if we sample with replacement with respect to order, that gives us size of the sample space as n to the r, which is 6 squared, or 36 total outcomes. Well, that looks good because we had a 36 in our answer. And E was we get at least 1/6, right? So we could get, the second one could be a 6, 1/6, 2/6, 3/6, 4/6, 5, 6. Of course, we could get 2 6s, or we can get 6 as the first row and not the second one. Let's enumerate or write out those possibilities. And so in total, we get the size of E is 1, 2, 3, 4, 5, 10, 11. And so it looks like the probability of E would be 11/36. And that certainly follows with what we got solving this problem using independence. Notice in my counter perspective, I never said anything about independence. But by solving it in this ordered way, I seem to have got the same thing as if I had solved the problem assuming independence between the roles. Okay. So the other way we could solve this is unordered. Right? So in that case, size of S is, well, so now I'm sampling with replacement without order. So our formula says that this should be n plus r minus 1 choose r, which is going to give us 7 choose 2, or 21, to do that, outcomes. That's different than 36. And E, in this case, is the unordered outcomes, 1/6, or 6/1, but there's no difference now, all the way up to, let's say, 5/6, or 6/5, and of course, 6/6. So in this case, the number of things in E is, what do we get? We get 6 total. So in this case, we get 6/21 as a probability. So that's very much different than 11/36, which we got. So this is an example, not rigorous proof, of why when we're kind of assuming independence, we are tacitly, when you're solving a counting problem, if you're kind of assuming independence among these things, then probably solving in this ordered way is the way to go. That will give you the answer that comports with the independence, whereas solving the unordered way doesn't. Not a universal theorem that's always true, but just generally it's a thing to keep in mind, right? Which is that, are the samples, is there some kind of independence I'm supposed to be respecting here? So we can look at kind of another kind of even simpler example to break down a little bit of what's going on here. So again, I could say roll 2 dice, and maybe E is I get a 1 or 2 on the first roll, and a 3, 4, or 5 on the second roll. Okay. Now, if I have independent rolls, so these things are independent, here's how I can think about the problem. I have a basket with 1, 2, 3, 4, 5, 6 in my basket. I'm going to sample one of these out of the basket, right? So I'm going to take 6, maybe. That's my first one. Doesn't really matter. And then I'm going to replace it. So this is going to step 1. But I sample with replacement. And so I put the 6 back. And I'm going to sample something else. So maybe I sample 1 the second time. So the probability, for example, that, let's say I get the event that is 6 and then 1. There's a sample of 6 on step 1, And on step 2, I sample a 1. Well, if these things are independent, I have a 1/6 chance of sampling 6 on the first time, and I can multiply because things are independent, and I have a 1/6 chance of getting a 1. The probability that I get 6/1, 1/6, or 1/36, right? And okay, so let's go back to my actual event we're going to look at for this problem, E here. So if I count in an ordered way, say, then how many events are in S? Well, we said we've done this several times. There should be 36, right? There should be n to the r, which is, in this case, n squared, so n by n, and n is 6, so 6 by 6 is 36, right? And how many things are in E? Okay, well, E is the set that contains, for example, if I'm counting in an ordered way, that set that contains everything where I have a 1 or a 2 on the first and a 3 or 4 or 5 on the second. So it's like 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, right? That's my event E. 1 on, or 2 on the first and 3, 4, or 5 on the second. Yeah. Okay. And so I could actually write this, sorry, that's E, not the magnitude of E. That's E. That's actually just a Cartesian product. It's the set containing 1 and 2, Cartesian product with the set containing 3, 4, or 5, right? Cartesian product is all ordered pairs, 1 from the first, 1 from the second. And so the number of elements in E, which we can count as 6, is the number of elements in this Cartesian product, which is number of elements in 1, 2, times the number of elements in 3, 4, 5. So you can always do that. The number of elements in Cartesian product, as long as the sets are finite, is just the product of those number of elements in each. And that's 2 by 3, right? That makes sense. And so probability of E is what? It's 2 by 3, number of things in E, divided by 6 by 6. Or it's 2 over 6 times 3 over 6. Why do I write it that way? Well, look, 2 over 6 is the probability of 1 or 2 on the first, and 3, 6 is the probability of 3, 4, or 5 on second. And so if we assume these are independent, we're just multiplying the probabilities of the two independent roles. So just to kind of reveal what's going on behind the scenes here is the reason that the unordered counting has some kind of multiplicative structure often when counting the outcomes. And so that multiplicative structure is going to basically give us another way of thinking about independence, which also has a multiplicative structure. Now, if I were to do this problem, but I were to change out the top and the bottom for counts where things are unordered, I wouldn't necessarily get this kind of nice multiplicative structure. And therefore, there's not really a way to interpret it as independence. And so that's kind of, some examples of independence, but that's kind of what's going on behind the scenes. So I made this kind of slightly cryptic comments a couple lectures ago about, okay, when you're counting and you typically want to do it in an ordered way to respect the independence, your mileage may vary depending on the exact problem. Now that we actually know what independence is, you can actually see what's going on. It's because often, not always, but often that kind of multiplicative structure that we get out of assuming independence of certain things is respected by the ordered counting. Now, if this problem is sampling with replacement, basically, because I put the item back in my basket when after I draw. If you're solving without replacement, actually the kind of two approaches are going to give you similar answers, because the top and the bottom are just going to be kind of multiples of each other. So it's not going to matter as much. Okay. So that's enough belaboring of that point. But hopefully that will head off some potential confusion on those problems. It can seem a bit hard to figure out, do I solve this in ordered counting or unordered? And so just think about independence, think about equally likely outcomes, and see if you can reason your way to which one's going to respect those correctly. Okay, let's talk about some theorems of independence. So complementary independence. So complementary independence says that is a theorem that tells us how independence interacts nicely with complements. So let's say if A and B are independent events, so let's just say A per B, then we kind of have a laundry list of other events that are independent. A is going to be independent of B complement. B is going to be independent of A complement. A complement is going to be independent of B. And A complement is independent of B complement. There are kind of four possibilities, complement or not. And turns out they're all independent. If A and B are independent, you can take complements of anything and you still maintain your independence. That's super nice. And that makes sense, because if the complement of something affected probability of something else, it wouldn't make sense that the original thing didn't. They kind of sum to one. We know that. Okay, let's look at a proof of why this could be true. And we're just going to prove case one. The other proofs are kind of really similar here. Okay. So we want to show that A is independent of B complement. How do we show that? In order to show that, we need to show that A, B complement equals, and we're going to have some chain of equalities, and at the end of the day, we better be able to show that this is probability of A by probability of B complement. So, first of all, right, so if we can establish that, we establish independence. So first of all, let's show that, let's use a little theorem that says we can write P of AB complement as probability of A minus probability of AB. And we justified that maybe in the second lecture when we're talking about some of the basic theorems. And by doing that, since we know A and B are independent, we can break up that A intersect B as probability of A by the probability of B. And then we can factor out probability of A. So we get probability of A by, 1 minus probability of B. And of course, 1 minus probability of B is probability of B complement. And so we've shown exactly what we want to show, which is that we have that kind of independence, then we can complement kind of arbitrary events and still maintain independence. Okay, that's a nice little helpful theorem. So we originally had this definition of independence. So if we scroll way back up to the top here, we had this definition of independence that was this multiplicative thing. So that A and B are independent if we can kind of distribute probability over intersection in this kind of multiplicative way. And that seems like a weird definition of independence, given that the real intuition we have was this theorem, which said that really want to say is that the conditional probability is kind of unchanged if we condition on an independent event. And the reason why we go with this multiplicative definition instead of, one of the reasons why we go with this multiplicative definition instead of this kind of intuition is that it generalizes much more easily. Not that you couldn't come up with a definition of independence otherwise, but it allows us to very straightforwardly generalize independence to multiple events. So independence of multiple events is called mutual independence. Oftentimes we will drop the word mutual, but this is really what we mean. So this is kind of a formal way. So mutual independence is going to generalize independence to multiple events. Okay. What's the definition of mutual independence? So first of all, we're going to assume we have, let's say, some set, some sequence, I goes 1 to n, of events. Man, that's not a sentence. If a and ai are events, we say they are, and we'll put in parens, mutually independent. If, and here's where the definition gets a little more complicated, if for any subsequence let's say a sub I1, a sub I2, all the way up to a sub I k. This is just an arbitrary notation for some subsequence. Could be A2, A7, A8, A11. It could be any length. Here our length is k, but the i's are just I1, I2, etc. are arbitrary indices. So if any subsequence, so this is a subsequence of length k in this case, but the length doesn't matter. For any subsequence, we basically have a similar multiplicative rule. That is, for any subsequence of my original a sub i's, the probability of the intersection of this subsequence, so this is intersection of the a sub ij, that a sub I1 intersect a sub I2, intersect all the way up to a sub ik. And can you guess what this is? This is the product, so capital Pi for product. J goes 1 to k of the probabilities of these events. This is supposed to be a sub I j, a sub I sub j, like that. Okay. So this is kind of our definition of mutual independence. It generalizes independence from just two events to multiple events. So examples, in order to check mutual independence, right? So the definition says that for any subsequence of any length, this multiplication, this product rule holds. So if I gave you a sequence of events, typically, you would have to check that for every subsequence of any possible length, the multiplicative rule holds, right? So for example, I would have to check that the probability A1, A3, A4 is probability of A1, probability times probability of A3 times probability of A4, right? But I would also have to check that probability of A2 intersect A7, intersect A11, intersect A12 also follows this multiplicative rule, that I can write this as the product like this. I can write etc. So given a sequence, you'd have to check this for all possible subsequences. So it can be a kind of in some ways, it can be good and bad. It can be really onerous to check generally, but it's a very powerful condition if you kind of assume it to be true, a mutual independence. Okay. So a natural question here is, there are a couple of natural questions. And one natural question is, oh, maybe I can phrase it this way. Do we really need to check? We need to check all subsequences generally. Maybe can I just check instead that the probability of A1, A2, A3, ... intersect up to AN? Can I just check that this multiplies out with this probability of A1 by A2 up to probability of A sub n? All right, can I just check that? Because that would be a lot easier to check than having to check every single subsequence. Fortunately, the answer is nope, you can't. So in general, you have to check every subsequence. We can look at an example of this. This will be a nice little example of independence of two events at a time and of mutual independence or not, and why you really have to check all possible subsequences. Okay, so let's look at an example. Roll 2 dice, my favorite experiment here, and let the event A be the event I get doubles, B be the event that the sum of the 2 dice is between, let's say 7 and 10 inclusive, and C be the event that the sum is 2, 7, or 8. It's a bit of a contrived example why I want to look at these. Not really obvious, but it'll show kind of nicely what's going on here, or kind of a counterexample to the hopeful above rule. Okay, so what are doubles? So I roll 2 dice. What are doubles? It's 1, 1, 2, 2, etc., all the way up to 6, 6. And so the number of things in A is, of course, number of things in A is 6. The sum is between 7 and 10. Ooh boy, that's going to take a lot to enumerate. Let's move this thing down here. Oh, come on. Move this event down. So the sum is between 7 and 10. What are the possible outcomes there? Well, I can get 2, 5. I could get 1, 6. I can get 3, 4. 4, 3. 5, 2. 4, 6, 1. Right? Those are all the 7s. I could get 8, which is what? 2, 6. 3, 5. 4, 4. 5, 3. 6, 2. So the 7s, 8s, 9s, 3, 6, 4, 5, 5, 4, 6, 3. Or I could get 10. Keep moving this thing down. I could get 10, which, of course, just double 5s. How many events do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Is that right? Seems like I'm missing something. Oh, I could, of course, I want to get 10. Of course, I can get 6, 4, 5, 5, or 6, right? There we go. Now we have 18 outcomes there. And C is the sum is 2, 7, or 8. So I'm not going to rewrite all of them. I'm going to say 7 line, the 8 line, and in addition, here the sum is 2. That's just 1, 1. And you could count up all those outcomes, show that the number of things in C is 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. Okay. So here are my 3 events. And the question I want to answer is, are these mutually independent? So to check they're mutually independent, I have to show for all possible subsequences that my multiplication rule holds. Right? So for example, if I look at probability A intersect B intersect C, that better be the probability of A by the probability of B by the probability of C. Right? That's one subsequence I have to check. Well, is it true for that? Let's check. A intersect B intersect C. What's in all of them? 1. Nope. 1's not in all of them. So let's just think it has to be a double. Some has to be between 7 and 10. And some has to be 2, 7, or 8. I think that leaves 4, 4. So I think ABC is just the doubles 4, 4. And so the probability of 4, 4 is, of course, 1/36. Probability of A is 6/36. We have 6 things in A. And we can multiply these. Probability of B is 18/36. And the probability of C, 12/36. And that simplifies to 1/6 times 1/2 times 1/3, which is indeed 1/36. So it checks out that probability of A, B, C, probability A intersect and B intersect C is the product, probability A by the probability B by the probability C. Unfortunately, that's not all we have to check, right? It'd be nice if that's all you have to check for mutual independence. You actually have to check all possible subsequences. This is true. So consider the event BC. B intersect C is basically that the sum is a 7 or 8, right? B is that the sum is between 7 and 10. C is that 2, 7, or 8. So that leaves us with 7 or 8. And so the number of things in BC is 11. You can count that. And so the probability of BC is 11/36. Now what we want is that this is the probability of B times the probability of C. So can I point out something that might be a sign this is not going to work out? All right. 11's prime. We're going to have to factor that. That seems like it's not going to work well. And indeed, we know that the probability of B is 1/2, and the probability of C is 1/3. And so this side is 1/6, which is definitely not 11/36. So the check fails for subsequence B, C, let's say. And so they are not, so A, B, C, not mutually independent. So why am I making a big deal of this? One of the question is, well, why can't we just not check for everything? Why can't we make up a new definition of independence where we only have to check for all events together? We don't have to check for every possible subsequence. The reason we don't like that definition of independence is that if that would mean that we could have a set of events that are independent with a subset that are not independent. And that seems weird to us. That doesn't comport with our intuition about what independence is, right? If I have 3 items that are independent and I remove one, I expect the remaining 2 to still be independent. So this product rule holds for 3 events at a time, but if I remove one, if I remove A, it fails. And so that would be weird if you could have a subset of independent events that aren't independent. Like if I have a set of linearly independent vectors, and I remove one, the remaining set is still linearly independent, right? That's kind of this word independent in mathematics. That is one of the things that's almost always true when you use the word independent. And so that's why we insist that all possible subsequences are independent. There is kind of a watered down version, and that's really not used as much, but we can talk about it real quick. It's called Pairwise Independence. And pairwise independence of a set of events is what it sounds like it is, which is that we say some sequence A sub I are pairwise independent if our kind of independence multiplication rule holds for all pairs. That is, the probability of AI intersect AJ is the probability of AI times probability of AJ, or I not equal to J. So not nearly as commonly used. When we talk about just say independence of multiple events, we always mean mutual independence unless we specify. Occasionally people will use this pairwise independent, but it's a bit of a strange creature. An interesting thing to note here is that I had to specify here that I is not equal to J. Is that necessary? Can an event A be independent of an event A, of itself, for example? Is it events generally independent of themselves? Well, the layman's kind of intuition with independence says that generally events wouldn't be independent of themselves, right? I know A occurred, surely I know A occurred. And so I have a lot of information about it. The occurrence or not of A should not be independent of itself, not be independent of the knowledge that A occurred or not. When does the intuition break down? Well, when does knowing whether or not A occurred not actually tell me anything more about the event? That will kind of, the intuition is that's going to break down when we either know A always occurs or it doesn't ever occur. That is when the probability is either 0 or 1, then knowing anything about whether or not A occurred, and you always know it always occurred or you know it never occurred. So can we formalize that? Well, if A is independent of A, then surely A intersect A should be the probability of A by the probability of A, which is the probability of A squared. And of course, A intersect A is just A. So we get a relation here that says the probability of A is the same thing as the probability of A squared. And the solutions to this equation with numbers between 0 and 1 says that, well, what solved this? A better either be 0 or 1, right? Because, sure, 0 squared is 0, and 1 squared is 1. So two examples are the null event is independent of itself. The whole sample space is independent of itself. Those are not the only events. Any event with probability 0 or 1 is also going to satisfy this. Interestingly, the null event presumably is independent of all events, right? Because, well, I'll let you think about why that's true, right? Just use our definition. So a question is, which I've kind of hinted at the answer, pairwise independence. Is that equal to mutual? Maybe it's enough to check all pairs. And I think, you can kind of reason there with some logic about why that might not be true. why you can, if just checking all pairs isn't going to ensure that any possible subset is going to be independent. But it's not super, super trivial. So, I mean, the answer is no. And so let's do a little example. This will give us some more practice with independence. So again, it's a bit of a contrived example, but let's look at it. So we're going to have our sample space be kind of a couple different kind of triplets of letters: AAA, BBB, and CCC. And then permutations of A, B, and C: ABC, BCA, ACB, CBA, BAC, CAB. Right, so it's AA, BBB, CC, and then permutations of A, B, and C, right? How many permutations of 3 letters there are there? 6. 1, 2, 3, 4, 5, 6. So we're good. And let's assume all outcomes in S are equally likely. Notice that S has, 9 elements in it. So each of these possible outcomes, which are just, they're nothing more than strings of letters, right? Not intersections, nothing more. They're just strings of letters. And each of these has probability 1/9. So furthermore, we're going to define the event capital A sub I to be the event that the ith place in the triplet is on A, right? So A sub 1 is all those triplets where the ith thing isn't, where the first thing is an A. So AAA is surely in there, ABC, and ACB, right? A2 is all things where the second thing is an A, which is what? Let's see, which ones have the second one as an A here? BAC, CAB. Oh, and again, AAA, of course, has A in the second place also. And A sub 3, AAA, A is in the third place there, and we get BCA and CAB. Oops, I'm sorry, and CBA. And so notice that the probability of any of these individual A sub I each have 3 elements. 3 out of 9 gives us a third probability each. Furthermore, if we look at AI intersect AJ, this is just going to be the triplet AAA. So what this means is that if we want to pairwise check this independence rule, then we know that the probability of AI AJ is 1/9. And the question is that probability of AI times the probability of AJ, which is a third by a third. That looks like it works out. 1/3 squared is 1/9. And so this independence rule works. So what we can say is that pairs are independent. Okay. However, if we look at the intersection A1, A2, A3, this again, intersection of all 3 is just again the event AAA that has a probability of 1/9, and that certainly is not equal to probability of A1 by the probability of A2 by the probability of A3, because this thing is 1/27. It's 1/3 by 1/3 by 1/3. So this thing fails for 3 events, and therefore these events are not mutually independent. Nonetheless, they're pairwise independent, but pairwise does not clearly imply mutual independence because we have now constructed an example here where they are pairwise independent, but they are not mutually independent. So unfortunately, we're kind of stuck in general with this mutual independence rule. And it is what it is, as they say. Yeah, so typically we're going to have to check all pairwise events. Okay, let's look at an example of where mutual independence can be helpful. So let's say failure. This example is an example of failure in a serial system or serial circuit, you can think of it. So here's our system. It has a series of components. So it's serial. Component 1, which then feeds into component 2, which feeds into component 3, which feeds into component n. So we have n components. These are my n components. And each of these components has a failure probability of p sub I. So the failure probability of component 1 is p1, the failure probability of component 2 is p2, p3 is the failure probability of component 3, all the way up to p sub n. Now, what we're going to say is that the system works only if all components work. Right? It's a serial system. You can't go around it. You have to go sequentially, serially, through each of the components. So if one of them fails, the system doesn't work. And we have all these failure probabilities for each of the components, and we can assume that the failure of the components is independent. Now, whether or not that is, that's supposed to read independent. Let's try that again. Whether or not that's a reasonable modeling assumption depends on the system. And that's a kind of operations research question. The simplest model is say, okay, the kind of naive model, say that they are independent. So what I'd like to do is calculate the probability that the system works. That's clearly what we know, or the probability the system fails, which is going to be 1 minus that. So we can do this by letting f is that the notation we want? Let's say W for works. W sub I is the event that the ith component works. Okay. And we know that the probability of Wi complement, which is the probability that the ith component fails, is going to be P sub I. And we can rewrite this kind of in proper set notation. The probability, the event that the system works is going to be the intersection between the W sub I, right? It's going to be intersection I goes 1 to n, W sub I. The first one works, and the second one works, and the third one works, and the fourth one works, etc. Right? And if these are all independent, so with the failure or not, right, are independent, so the W sub I are independent, or their complement, we know we don't care because we know that we can take complements and not change independence. We proved that. Then I can write this there. When I say independent here, this means mutually independent, right? So I'm just kind of lazy. I don't want to say mutually independent, but we're talking about more than one event, so we mean mutual independence. If these things are independent, we can write this as the product of the probability of the W sub I. And we don't actually know the probability that each component works. What we do know is that the probability they fail, or W complement, so we can write probability W sub I as 1 minus probability W sub I complement, and we know each of those is P sub I. And so this gives us our formula, which is 1 minus P1 times 1 minus P2 times 1 minus P3, 1 minus all the way up to Pn. Right? So this is basically like almost like an average in some ways, but it's kind of a product instead of a sum. And this kind of thing, if you take a, say, operations research class, then this kind of product will come up quite a bit. The way we get the formulas through this independence. And so that's kind of a nice little example of independence there. So I'm going to stop the lecture there. I think we're a little under time today, but we went a little bit long last time. So just as a recap, we talked about independence today. We talked about the formal definition of what independence is. We talked about some intuitions. We looked at some examples and talked about its relation to how we solve some of the counting problems. And we looked at some examples there. We talked about a theorem about complementary independence, saying we can take complements and that doesn't change whether or not events are independent. And then we generalized to a definition of mutual independence. And mutual independence says that every subsequence of a set of events must be independent. The idea being that if I have a set of mutually independent events, they respect the product rule, and any subset, if I remove any of them, the set is still independent. And we looked at some other, well, basically we showed that you really do generally have to check all possible subsets. You can't just check the intersection of all of them together, and you can't just check that things are pairwise. And so we showed some examples here about pairwise independence and other things, and how these they're not the same concept. And then we closed off with this example. So this is through the first major part of this course, talking about some kind of the basic concepts of random variable, not random variables, of probability. Next time, we will start talking about random variables, and this will allow us to talk about probability in kind of a more algebraic language that we're used to. So stay tuned.